In this video, we're going to start talking about a new technique for solving differential equations. The differential equations it works on are the ones that look maybe like d squared y by dx squared minus 5 dy by dx plus 6y equals 0. So what can we say about this differential equation? Well, it's second order, as it's got no derivatives of y beyond the second derivative. It's linear because every term has at most one y or derivative of y in it. No y squared or anything like that. It's homogeneous because every term has exactly one y or derivative of y in it. And it's got constant coefficients. So the numbers, well, 1 here, though we don't write it, minus 5 here and 6 here are all constants. So this is a technique that's going to work on second order homogeneous linear differential equations with constant coefficients. That seems like a lot of words to remember, and of course it is, but don't worry, you'll come to recognise it as working on the differential equations that look a bit like this. So the technique turns out to be more or less to guess a solution, and the right thing to guess first is pretty much always the same. You guess that the solution might be an exponential, so we guess that y equals e to the kx, for example. Now, the aim is to substitute this back in to form an equation for k, so we can find out what k would have to be if this were in fact to be a solution. So if y is e to the kx, then dy by dx is k times e to the kx, and second derivative of y is k squared e to the kx. So if we substitute in, we find that k squared e to the kx minus 5k e to the kx plus 6 e to the kx equals 0. We can divide out all the e to the kx's because they occur in every term, and so we find that k squared minus 5k plus 6 equals 0. That's of course just a quadratic equation for k, and moreover it's a quadratic equation whose solutions we can see just by factorising it in our heads. So this quadratic equation factorises as k minus 2 times k minus 3. And hence k is either 2 or k is 3. So this tells us that there are two solutions to this, namely y equals e to the 2k and y equals e to the 3k. Y equals e to the 2x and y equals e to the 3x, of course, I mean. That's only two solutions. We should ask ourselves, can we find more? Are those the only solutions? Are there more lurking? And in fact, there are many more out there. What we can do is we can take linear combinations of these two solutions. What I mean by linear combinations is if we try y equals a e to the 2x plus b e to the 3x, so some multiple of this solution plus some multiple of this solution, then we're going to get a solution to this differential equation as well. Let's just check that to be sure. So we find that dy by dx equals 2a e to 2x plus 3b e to the 3x. And if we differentiate again, we find that d2y by dx squared equals 4a e to the 2x plus 9b e to the 3x. Then if we substitute all these back into this equation to check that it holds, we can check the e to the 2x terms and the e to the 3x terms separately. So for the e to the 2x terms, we get 4a from the d squared y by dx squared minus 5 lots of dy by dx, so that's minus 10a, plus 6 lots of y, which gives us plus 6a times e to the 2x. And if we work out the e to the 3x terms, we get 9b from the d squared y by dx squared minus 5 times 3b, so that's minus 15b, plus 6 times b, all times e to the 3x. And of course, 4a plus 6a minus 10a is 0, and 9b plus 6b minus 15b is 0, so we get 0 as expected. This is a general feature of equations like this, homogeneous linear differential equations with constant coefficients. If we take some solutions, if we take linear combinations of them, we can find more solutions. So this is a good way of getting a general solution to an equation of this shape. I'll do another example where the quadratic turns out a little nastier. So let's do another example. Let's do d squared y over dx squared minus dy by dx minus y equals 0. What can we say about this one? Well, again, if we guess that the solution is an exponential, e to the kx, say, then we can form an equation to find out what k has to be. Again, of course, we get dy by dx equals k e to the kx, and d squared y by dx squared equals k squared e to the kx. So our equation becomes k squared e to the kx minus k e to the kx minus e to the kx equals 0 when we substitute in our values for y, dy by dx and d2y by dx. As we had before, we have an e to the kx term everywhere here, so we can divide it out and we get k squared minus k minus 1 equals 0. This is a quadratic equation for k again, but it's a bit more complicated. We can't factorise this one just by looking at it. Instead, we'll use the quadratic formula. So when we use the quadratic formula, we get that k equals minus the coefficient here, so that's 1, plus or minus the square root of the square of the coefficient here, so that's 1, minus 4 times this coefficient, which is 1, times this coefficient, which is minus 1, so that's minus 4 times minus 1, that's plus 4, all over twice the coefficient here, which is 2. So that's 1 plus or minus root 5 all over 2. And again, if we go through the check, we'll find that not only do these k's work, but any linear combination of e to the kx for either of these k will work. So the general solution of this differential equation turns out to be y equals a times e to the 1 plus root 5 over 2x plus b times e to the 1 minus root 5 over 2x. So that again gives us a two-variable family of solutions to this differential equation. We choose any constant a, we choose any constant b, and we substitute in, we get a solution to this differential equation. So we have a two-variable family. In the next video, we'll start talking about more examples of this and what happens when we have complex roots.